Right, so in the previous session, we talked about starting of DC motors, right? So we said when you are starting a DC motor, the back EMF will be equal to 0. Right, your back EMF will be equal to 0. So if your back EMF is equal to 0, from the previous equations, we realize that the value of the field current or the armature current, whichever way, will be solely dependent on the value of the terminal voltage and the armature resistance. So we said in order for us to be able to control the current so that it doesn't go beyond what our windings can manage, since we said RA is normally very small, so that we have a small armature drop. Then we add an external resistance, RA external, which will help us to control the current. So we say this mechanism is achieved by adding external resistances, then we remove them slowly as the speed picks up. That's why we're saying you can move from the off position to position number 1, right? Then you move from position number 1 to position number 2, and in that case, you are removing the resistances slowly. You are slowly removing the resistances. So at the end of the day, at position number 5, you only have the armature resistance as the drop, and in that case, you've properly managed to control your startup current, right? So moving your handle between these resistances and monitoring the startup current so that it is not excessive, right? So that it is not excessive. That's the mechanism. Then the last type of motor that we are going to look at is the permanent magnet DC motor. As the name implies, this motor is a permanent magnet. So as you see, previously we were discussing motors that use electromagnets to produce the required magnetic flux. But then in this situation, in the permanent magnet DC motor, instead of an electromagnet, we have permanent poles or permanent magnets. That means we have an almost fixed flux in the air gap because of the permanent magnet, right? So because we have a permanent magnet, that means we don't have a field circuit to talk about. There is no field current to talk about. So the permanent magnet will now replace the field circuit. But then on the side of the armature, it is normally on the stator, on the rotor, sorry. On the part of the armature, we still have our armature windings, right? We still have our armature windings. So what we'll be having will be current flowing only in the armature windings. Then as the current flows, it interacts with the magnetic field produced by the permanent magnets. So this is our air gap where the flux will be radiated into the armature, right? And then this will be carrying current, right? So we only have current in the armature circuit. And hence, it's called a permanent magnet DC motor. It is a DC motor because the armature winding is connected to a DC terminal. So the absence of the field windings means we have less copper losses. So the IF squared R losses are no longer there because we have the permanent magnet. The motor, because of the absence of the field windings, it can be small and cheap because it doesn't need space or material for field winding. That means you don't need more copper for your motor. You don't need more copper for your motor. But because of the difference in magnets, you might find out that some motors may become more expensive due to the use of expensive magnets. So you can see that we have several disadvantages of this motor. Besides it being smaller and cheaper, it may be demagnetized when there is excessive armature current or when there is overheating. That means the core might be demagnetized when there is excessive heating or excessive armature current. How does excessive armature current demagnetize the poles? Remember, we said when current flows, it is an associated magnetic field. So that magnetic field, we realize that that magnetic field gives us the armature reaction, and then that reaction will produce a flux that tends to oppose the pole flux, and resultantly it might demagnetize our poles. And also permanent magnets, they have limited flux density. You can't compare them to the electromagnets. Why? Because one, for a material to have a permanent magnet, that means it should also have a large what? Hysteresis loss. That means it also has a larger reluctance. So resultantly, the flux then that can be established is also limited. And also the control of this motor is limited to the armature. Because if you have a permanent magnet, there's no way you can control it. So you have to control it through the armature characteristics. That's the terminal voltage or the armature resistance, which will control the armature current. They also best operate at low speeds and cannot be operated beyond the base speed. So when you talk about base speed, you are talking about the rated speed. So normally you can't achieve that. Remember, when we're talking about our other motor, let's go back slightly, we realize that the control beyond base speed is normally achieved through field control. Now, because there is no field to control because of the permanent magnet, you cannot operate that motor beyond the rated speed. And also, because of the need for bulky magnets and the like, they are also limited to small fractional horsepower applications. So permanent magnet motors are normally used for smaller applications, like the wipers and so on, which need small power. Basically because of the limited flux density. But the advantage now is that they can be powered using simple battery sources. That means you can actually use that permanent magnetic motor using a simple battery source. But then if you can get bigger magnets, again, you can still use them for larger applications, though with limited control characteristics. So that brings us to the end of our DC motors. Then the next thing that we are going to be looking at is we'll be looking at AC generators and AC motors in our next lecture. So as of now, we can look at that and also go back and read and do the worked examples, which I have not included in this lecture. We do the worked examples. Unless if you have questions. See, very few people, no problem.